Hi, this is lecture 11, and in this lecture we are finally going to start asking questions about, well, what causes things to move or change their motion rather than just trying to describe it. So we're moving from kinematics onto dynamics. The first question we have to ask in this context is, what is a force? Forces are going to be the central concept that will help us understand what makes things change the way they move. So here are some things we're going to go through in this lecture. It should be fairly conceptual and hopefully not too long. So we're asking, what is a force? Sounds very simple, and the answer is fairly simple too, but perhaps a little bit more subtle than one might think. We're going to give some examples of forces, and we're also going to just briefly comment on this thing about those 4 fundamental forces that you might have come across if you like reading, for example, popular physics magazines where it tells you about the latest discoveries from this or that particle accelerator or whatever theory physicists have come up with. Often you come across this idea that there are 4 fundamental forces. Well, what does that mean? It's not really part of our course, but I think for context we're just going to mention that in passing. We're going to talk about Newton's third law. Yes, we'll also talk about the first and second law, but we'll do that a bit down the line. I think this one, actually, in a sense, is the most important one to understand what a force is. And we'll see how forces are represented as vectors. We state the cause acceleration, though we don't go into detail quite yet. We'll come back to that in the follow-up lectures. And we'll talk about the concept of a net force. Again, we're laying a lot of the groundwork here for actually applying a more systematic treatment of forces. Okay, so let's start then with the basic question. So what is a force? And one answer you might come up with, and I think even the textbook sort of answers it's something like that, is it's some kind of push or pull that's acting on an object. And in a way, that is fair enough. There could be many ways something could be pushing or pulling. Maybe you tie a rope to it and you pull on it. Maybe you push with your hands. Maybe you touch some kind of rocket thruster. Maybe it's just being gravitationally pulled. Whatever it is. So if this is fairly general, then yes, this is actually not a bad characterization. But we can do a little bit better. So when you think about some things that are being pushed or pulled around, just in your mind, try to think of something that's getting pushed. Well, there is necessarily something else there that is doing the pushing or the pulling, right? So, let's write this down. But we also need, can't write today, need something else or someone else doing the pushing or pulling. And if you think about this carefully, right, if you try to pull on a rope, for example, you can feel that you're pulling on it hard. It's like the rope trying to pull you back. And maybe if you imagine you pull on a rubber band, you stretch it, well, the rubber band is pulling back on you. There's always this two-way effect. And it's going to be the case no matter what type of force you're thinking about. So the key really is, instead of playing a guessing game, what are forces, let's just state the answer. Forces, fundamentally, they are interactions. That's the key understanding we need to have. So we can imagine, if you want to come up with some theory of the world, you might say, okay, what things are there, and then what do those things do, and specifically how do they affect each other. And that how do they affect each other, well, that's what interactions are about, right? So forces always affect each other. It's a two-way process at all times. So we want to say forces don't act on objects, they act between objects, right? Forces act between objects. So you might say there's a gravitational pull between the Earth and the Moon, and it affects both the Earth and the Moon. Maybe not equally, doesn't affect them equally, right? Because they're different objects. but it's always a two-way process. Okay, so let's think of some example and just see what it actually means. This was a bit abstract. So let's think of some examples of forces. And maybe right now you want to just pause the video and just write down some ideas. Well, here I go. I'm going to write down mine. Well, one thing I can definitely think of is gravity, right? Because it's been pulling already in our class. The force of gravity on something is also often called the weight. And we'll go into that, of course, in more detail fairly soon. Maybe another force, very simple. I push something by contact. I'm not sure what to call that. Push something with my hand or with my foot. But the technical term here is going to be, it's a normal force. What's normal about it? Well, I'm going to tell that to you in a couple of lectures from now. A normal force is a technical term for if you lean against a wall, for example, right? Or you push off something as you're jumping, push off the ground as you're jumping. Those are all normal forces. Maybe friction, right? Friction is one that definitely comes to mind. Friction slows stuff down. Or at least it tries to. For the most part. Air resistance, similarly, right? Why do parachutes work? Well, there's some kind of force going on. There's air resistance, air drag, as it's sometimes called. What else can we think of? Maybe electrostatic forces. If you take a balloon, you inflate a balloon, you rub it against the carpet, you hold it above your hair, it's like your hair stick up. Those are electrostatic forces. Or when you get laundry out of the dryer, often they sort of stick together and you can sort of hear the electricity as you pull them apart. Well, these are electrostatic forces that make your sock stick to your tablecloth. Or then when you just hold it near your skin, you can see the hairs on your skin stand up as they try to go towards the sock. So electrostatic forces, they seem fairly insignificant and fun, but actually they're crucially important, and they don't just affect laundry. They're like a fundamental force that holds the world together. And we'll come to that a little bit. And what else do we have? We've got magnetic forces. Your fridge magnet. Sticking to the fridge. Well, what is that? We can think about that. Definitely magnetic forces are involved here. The compass needle points north. Magnetic forces. Of course, again, there are a lot more fundamentally important examples than compass needles and fridge magnets. Tension. How about tension? Right? The tension, it could be tension maybe in a piece of rope. Right? You pull on a rope that allows you to pull on things that the rope's attached to. There's tension in the rope. Or maybe a rubber band. It stretches, right? The rope might not stretch very much, the rubber band might stretch, and you can kind of see how much tension there's in it by just seeing how far it is stretched. Another thing that has tension would be, for example, the spring, right? The spring you can stretch that might have some tension in it. Is that all? Maybe there's more. How about some pressure forces? So what I mean by that, well, forces, say due to air pressure or water pressure, sort of stuff you might treat in thermodynamics or fluid dynamics. Another important one we've mentioned is thrust, right? That's what makes your rocket go up, and so on and so forth. It's a long list, right? It's a long list of forces. It's not complete. But it definitely contains the main ones we'll be talking about in this class and possibly even in follow-up classes. So I said before that each force is really an interaction, right? Let's figure out it's an interaction between what? So some examples, and I'm going to put a little column here that says between what are this interaction? Well, gravity, for example, could be between the Earth and the moon. It goes both ways. The moon goes around the sun, right? But the Earth also gets moved slightly by the moon, and you can see the pull of the moon, for example, directly if you go down to the beach and you watch the tides, right? And a sort of side effect of the moon pulling on the Earth, even though you can't feel the Earth move as a whole, even though it also does. But also, for example, the Earth and you. When you jump, you fall back down. Why do you fall back down? Well, because there's interaction between you and the Earth. And actually, the Earth also gets pulled to you. Not very much. Well, the force is like just not big enough to move the Earth in any meaningful way, but it's technically there. We'll talk about it more a bit later in the course when we study gravity in general in more detail. What about contact forces? Well, this is kind of an easy one. If I push against the wall pushes back against me. The wall might hold you up, say your hand and the wall. Right, that would be one example of an interaction there. Or maybe the floor, right? Your feet and the floor. The floor, well, it pushes you up. It's kind of what stops you from falling, right? It counteracts gravity. But you also push down on it. How do we know that? Well, if you were the floor, you could feel somebody standing on you. And what about friction? Well, friction, maybe the examples we can think of, maybe car tires on the road. How about that one? Right, you're trying to brake really hard, you're sliding across the tarmac, while the car tires on the road. Friction ultimately brings you to a stop. Air resistance, but of course here the road and the car tires, they both act on each other. Is there force on the road as well? Is there force from the tires onto the road rather than just the road onto the tires? Well, yes. How can we tell? We can't really see it because the road is hard to move. It's attached to the Earth. But think, for example, if you jump onto a carpet, right? Say you run and you jump and you land on a rug, right? A rug. Now, the rug might bring you to rest. You don't just keep sliding across it, but you might also get the rug moving a little bit and slide across the floor underneath it. It's kind of a fun activity if you're a kid or even if you're an adult. So there you can see that the carpet, the rug is slowing you down, but you're also acting a force on the rug, making it go a little bit. So friction again acts both ways. Air resistance, air drag, well, maybe air, so obviously one of the two components here, one of the two partners that interact with each other is the gas itself. The air drag would also be water drag. So the air and maybe the parachute, right? And of course, the air slows down the parachute, but the parachute also drags the air with it. In electrostatic, we already had examples. Maybe it's your socks. Maybe it's sock on sock when it comes out of the dryer. Right? Or the balloon on hair. Makes your hair stick up. It's always two objects, right? Two things that are interacting with each other. Magnetic forces, well, what example do we have there? How about the fridge and the fridge magnet? Is it a two-way process? Again, this one's hard to see because you can't really see that the fridge magnet is also attracting the fridge, but you might use the same magnet to attract a little nail, for example, something light. And there you could see that the fridge magnet both gets attracted, but also is doing attracting. Tension, we already talked, say, about the rubber band. I can imagine I put two things on rubber bands, and then the rubber band tries to pull both sides of it in, right? So if I put my finger, if I have two fingers, maybe like this, I put a rubber band around them and I try to open them, I can feel a force on both my fingers. So the rubber band kind of acts as a force carrier between the two. Finger on finger, that might be an example here. Or a spring might be connected. You might have a little spring that's sort of hanging from a ceiling and there's a mass on it. Well, then the ceiling is pulling on the mass is pulling down the ceiling via the springs. Lots of examples there. Actually, this is a subject springs you're going to be studying a lot more detail in the sort of oscillations you get in a follow-up course. Pressure forces. Well, here maybe it could be water on a submarine. Right, high water pressure deep down. The water is pushing against the submarine. Is the submarine pushing back against the water? Yes, otherwise the water next to the submarine would, take up the space of the submarine. It would fill that space, but does the wall of the submarine is pushing back, for example. It's a bit more difficult to see the two-way process if one of the two things is a fluid, maybe like air or water. Thrust, well, this would be hot gas on the rocket, right? The thruster, engine having hot gas gets pushed out the back, while the hot gas pushes back against the rocket, pushing it forward. Just some examples. Whatever example you think of, maybe you can think of some others, just see what's interacting with what. And yes, sometimes you can't see the effect of the two-way interaction. Sometimes you can only see one side changing its motion, but it doesn't mean that the other side doesn't exist. So let's quickly answer then the question, well, what about those 4 fundamental forces? Now, if you've never heard of that, that's okay. Don't worry about it too much. But if you've ever read any sort of, popular physics magazine about the latest discoveries, the latest particle accelerator, talks about 4 fundamental forces, what's that about? Or more correctly, it talks about 4 fundamental interactions, right? But forces, we know, are interactions. So let's just state them. So one is gravity. That actually is a very fundamental force. In fact, it's a very special one, even among the fundamental forces, for reasons I'm happy to go into in class, but not right now, or this video might never end. In part, my PhD work is related to how gravity is special and problematic compared to the other forces. So I can actually go on about this forever and ever and ever and ever, and we'll never get anywhere in this course. So one of the 4 fundamental forces. Next one is electromagnetic interactions. So it turns out those electrostatic forces and those magnetic forces, they're actually aspects of one and the same. So indeed, this is again very important force. It makes our essentially, for example, it holds atoms together, right? Electrons, protons, the things that make up atoms. It allows molecules to form. This is all due to electromagnetic interactions. Gravity holds the universe as a whole together. Like planets stick together because of gravity. Stars exist because of gravity. Atoms and molecules exist because of electromagnetic interactions. There are 2 more. There's 4. So one is called the strong nuclear force. And the strong nuclear force is what holds atomic nuclei together. The protons and neutrons inside an atomic nucleus, they're held together not by electromagnetic force that wants to push them apart, but by what's called a strong nuclear force. But it doesn't really do much on larger scale. So it's kind of invisible to us. Because it all happens at such small scales, too small for us to see. And the other force is the weak nuclear force. And that is even more obscure. That has to do with certain again subatomic, subnuclear processes. And the most famous sort of appearance of it is in some nuclear decay processes. But it's sort of hard to put into words like what exactly it does day to day. I mean, it's super important, but it's hard to relate to in a sort of on an intuitive level. Of course, it is fundamental to what's called a standard model of particle physics. Without it, the world would look extremely different. It just wouldn't exist the way it does. Now, okay, so let's trust that physicists have figured out those are the 4 fundamental forces as far as we know it. Of course, there are open questions and so on. Very interesting stuff, but what about those other ones we've just mentioned? What about thrust and all those guys here, magnetic force, tension? What about those? Well, it turns out the forces that are not fundamental. So these 2 here, they together are one of the fundamental forces. Right? We experience them on a large scale where we can touch socks and the fridge magnets. They seem to be separate, but actually they're aspects of one and the same. Gravity is a fundamental one, right? So what about all the others? Well, it turns out pretty much all of them can ultimately be explained in terms of this one here, right? So my claim is that friction, contact, these normal forces like pushing by contact, air resistance, tension, thrust, all this stuff really comes down to being aspects of the electromagnetic force. And that is because if you zoom in on the, say, the atomic level, right? I want to say friction, right? You rub your hands together like this. You can feel friction is a force you need to apply to overcome. Push your hands together, apart, and forwards. Then you can feel you need a certain force to make it happen. Well, that is, if you could zoom in onto this sort of atomic and molecular level, you could see that is because of the interactions between the atoms on this surface and the atoms on this surface, and that interaction is ultimately electromagnetic. Tension, well, in a rope, well, what you're doing is when you say you're stretching a rubber band, right? You're really pulling apart those molecules, like you're stretching them. The molecules are held together by electromagnetic forces, right? Again, it all comes down to those. Or pressure forces. What are pressure forces? Well, in a gas, for example, or in a fluid, in a liquid like water, the atoms, the sort of molecules, are whizzing around in all sorts of directions, bumping into each other, and then they bump into, say, the outside of your submarine. And that's what's creating an overall force. Zillions upon zillions of tiny collisions. Well, those collisions are electromagnetic collisions. Right? So one atom doesn't just go through another one because they repel electromagnetically. So really, most of the forces we're studying, with the exception of gravity, are really deep down derived from electromagnetic interactions, which is interesting. It doesn't mean those are not real. It just means they're emergent forces. They can be explained in terms of something more fundamental, right? But tension is a thing that's out there. It's just we can explain it in terms of a particular application of electromagnetic forces. Now, if you're a particle physicist, you don't really care about tension and thrust. You care about what the world's made of deep down, and then you mention those four. Now, you ask a particle physicist, is friction real? And they will hopefully tell you, yes, it is a real thing. Right? It's just we can explain it in terms of one of those. Now, we're not going to worry about those. Like everything we're going to learn about forces applies to these. In a sense, it also applies to here, though. So they're better sort of mathematical descriptions, especially when we talk about those guys. So we're not really going to worry about this for the purposes of this class. But everything we're going to say does, in some sense, apply nonetheless. Okay. So those are the four fundamental forces. Let's not worry about them anymore. Put a line underneath. Let's take them, crumple up the paper, throw it out. Alright, so done. Okay. Where were we before that? We said forces are interactions, right? Let's write it down again. That statement that forces are interactions is summarized in what's called Newton's third law. Now, Isaac Newton, he worked in the 17th and early 18th century, and he is responsible in part for his development of essentially what we now call classical mechanics, the stuff we're learning right here, but also calculus, although he sort of co-developed it at the same time as Leibniz did in Germany, and there's some history there that's rather interesting and some more follow-up history. Very exciting stuff. But Newton developed the theory of mechanics, the stuff about forces and energy, and so on, that we're learning in this course. So Newton's third law, well, he had three laws of mechanics. We're going to start with the third one, and the third law essentially states, well, it states forces are interactions, but it states it in a more complicated way. It says that if object A acts a force on object B, and it doesn't matter what that force is, could be any type of force, then B acts a force on object A that is equal in magnitude, so equally strong, put this in parentheses, equally strong, but opposite in direction. This is Newton's third law. It's very important. Okay. Now, I think our textbook and many other textbooks tend to introduce this much later. Like, you talk about forces, you some calculations, and somewhere along the way you meet Newton's third law. I think it's extremely fundamental to understanding what forces are, that forces are interactions. So I'm going to state it first. So what it's saying is, if I push against you, you're pushing back against me with the same strength, but in the opposite direction. So let's do some examples of this where we can see this. For example, if you push with your feet against the edge of a pool and you're swimming. Against the edge of a pool, right? So you're pushing against the pool. Now you're trying to make the pool move. Well, it doesn't budge because it's touched the earth. The earth is big. But it also pushes back against you, and it actually propels you forward, right? So you can feel that. Or how about a car crashes into, I don't know, say a lamp post? What happens? Well, the car gets damaged, the lamppost gets damaged. They both experience a force, right? There you can see right away that the car that crashed the lamppost doesn't just act a force on the lamppost, it also goes the other way, or how else would it damage the car? We already talked about the rubber band. It pulls on both ends. Let me just write this down. You can't just have a rubber band that just pulls on one side. You stretch it, both ends get pulled inwards, and equally. And that's very easy to measure, actually, in that case. Gravity, we had already the Earth pulls on the Sun, or the Earth pulls on the Moon pulls back on the Earth, and so on. But I'm just going to put ... There are lots of other examples that we might come up with. Now, one thing you notice when you look at this is that, yes, forces, they have a direction and they have a magnitude, right? How strong and which way. That means they are vectors, or at least mathematically, they're represented by vectors. So, forces have a direction. Pushing something to the left is different from pushing it to the right. Gravity acts downwards, right? The world would be very different if gravity acted upwards. Forces have direction and magnitude, so this is just which way, it's fairly obvious. And then what is their strength, right? That's what we mean by the magnitude. So they are represented by vectors. Remember, vector, and draw it like an arrow, a certain force in a certain direction with a certain magnitude is represented by the length. Now, how do we measure the strength of a force? Well, the strength of a force, or the magnitude of a force, is measured in a unit called newtons. So same name as the third law that we just talked about. The same person, Isaac Newton. I'm not actually sure off the top of my head what Newton called the units of force. I doubt he called them newtons. He might have actually been working in sort of pounds. That the weight of 1 pound of stuff is like a unit, something like that, right? But the scientists, work in the metric units, and that is newtons. So I'll have to actually check Newton's work, probably the Principia Mathematica, to see what units he used. And we write this as the letter N. How much is 1 Newton? And let me say it's maybe about the weight of a medium-sized potato. I think that's a good sort of good estimate. Right, so you hold a potato in your hand. The force you need to apply to support it, to stop it from falling, that's equal to the force with which the Earth is pulling on it through the gravity. That's about 1 Newton. Like 1 potato, about 1 Newton. Now, what do forces do then? They change motion. We talked about this, like you saw yourself getting pushed off in the pool, or the rocket's accelerating because of the thrust. We're going to come to this, but I'm going to state it here. Forces cause acceleration. Right? Not so it's important, and for the longest time people were confused. They thought forces cause like velocity, like higher force means higher velocity. And there are reasons why it's intuitive, but it's wrong. Right? The only reason it's intuitive that you might think higher force means higher velocity is because there are things like air resistance and friction in our world that try to slow things down all the time. We'll talk about that in a lot of detail. But fundamentally, forces cause acceleration, and that will be explained in Newton's first and second law. And we'll talk about what the first law does specifically. It's actually more subtle than most people think. But this will all be subject of a future video. Okay, so basics of forces almost covered. There are a couple more things we want to talk about. And one thing we want to talk about is what happens if there's more than one force acting. What if multiple forces are acting on something? Well, if 2 things pull on something, what's the overall effect? The answer, of course, is it depends which way they're pulling. Are they pulling the same direction or the opposite direction? So, for example, I might have an object here. I'm just going to draw it like a dot. And then I have somebody pulling here. Let me draw a little person pulling here. Somebody else might be pulling here, opposite direction. I'm kind of imagining my 2 sons right now fighting over something. But what happens to the object? Well, what we have to do is we have to add those forces. We have to be careful when we do that, because we have to add them as vectors. So the direction matters. We know how to add vectors. The arrows tip to tail, for example. And worry about components, all that stuff, right? So, and we're going to do lots of examples. So right now I'm just giving you the grand picture, the overview. When you add all the forces, you're going to get what's called the net force. So adding all forces acting on an object gives what's called the net force. So the net force is not some new type of force, some new type of interaction. It's just a name for the mathematical sum of all the forces acting on an object. Right? So something might be pulling to the left, something else pulling to the right. Well, if those are equally strong, the net force would actually be 0. In general, we can write net force is the first force that's acting, plus the second force that's acting, plus the third force that's acting, plus however many forces that might be acting on an object. As vectors, so they can be positive, negative, to left, to right, up, down. They can cancel each other out. They can add to one another. It really depends on their respective directions. So vector addition is going to be super important. If you still feel a bit shaky about it, better go look it up. What we're going to be starting on next, though, as our first sort of approach to doing calculations with forces, is we're going to look at situations where the net force is 0. We'll do that in the next lecture, where the net force is 0. That's to say, all the forces acting are cancelling each other out, and so the object does not change the way it moves. So another way of saying the net force is 0 is that all forces get cancelled out by one another. In such a situation, we say the object is in mechanical equilibrium, but we'll define it again properly in the next video. Okay, so this was the rough and ready overview over forces. A lot of stuff that will go into a lot more detail, but hopefully you have a basic idea. Forces tend to be fairly intuitive, and then you can visualize it. You can visualize getting pushed around, but there are of course subtleties, and we'll talk about all of that. Alright, thanks for watching, and I'll see you in the next video.